The overall goal of this procedure is to array single neurons in two microfluidic compartments for the preparation of a connected neuronal co-culture. This is accomplished by first replica molding the microfluidic device in PDMS and encapsulating the device by plasma bonding. The second step is to pattern polylysine within the microfluidic device. This is achieved by filling the device with polylysine, allowing a water mass to form by evaporation, and then using a plasma treatment to remove the exposed polylysine to create the biomaterial pattern. Next, use a syringe to aspirate the neurons through the microfluidic circuit for single neuron arraying. The device is placed in the tissue culture incubator for neurite outgrowths to extend and connect the two populations of neurons. The final step involves using an aspiration pump to selectively treat one compartment and monitor the propagation of materials and pathology within the neuronal circuit.
Demonstrating the procedure will be Ya-Yu Qiang and Sarah Vida of the ISAS lab.
The main advantage of this technique over existing method, like commercially available PDMS component chamber, is that the neuronal co-culture are prepared with a single cell position for the analysis of individual neural outgrowths.
This method can help answer key questions in the field of neuroscience. For example, what is the mechanism underlying the propagation of hyperphosphorylated tau aggregates in Alzheimer's disease? Or how do infectious organisms spread throughout the brain?
The technique is ideally suited to high-throughput applications since only a few hundred neurons are required for each experimental condition.
Begin the procedure by mixing the PDMS pre-polymer thoroughly with the curing agent at a ratio of 10:1. Next, degas the mixture in a vacuum desiccator for typically 20 minutes. Then, place the two-layered microstructured SU8 wafer on an 80°C hot plate and align the polymer frames to each device on the wafer. Pour PDMS into the frame and allow 1 hour to ensure complete thermal curing. Once cured, remove the wafer from the hot plate and allow it to cool on a flat surface. Afterward, while wearing protective eyewear, use a rigid scalpel to gently prise the frame and PDMS from the wafer from one corner. Remove the PDMS mold from the frame and use a pair of scissors to trim the device. Apply the remaining PDMS to the entire wafer in order to protect it during storage. Upon peeling this PDMS layer off the wafer, any particulate contaminants are removed from the surface in readiness for repeat PDMS molding. Now, prepare the 6 interface ports using a 3mm biopsy punch, with the microstructured features facing upwards to aid alignment of the ports with the microfluidic channels. Inspect the device for particulates and remove them using reversible adhesive tape. Next, prepare a thin PDMS layer mounted on a glass cover slip by pouring a small amount of the PDMS curing agent mixture onto the petri dish. Press a cover slip onto the PDMS layer, place it on the hot plate, and thermally cure it for about 10 minutes. Shortly after cooling, and while wearing safety glasses, use a scalpel to prise the cover slip PDMS bilayer from the petri dish. To encapsulate the device, a good PDMS-PDMS bond is needed. Place the PDMS bilayer and the microfluidic device in the plasma oven for 40 seconds. Once plasma treated, press both parts together and allow to fully bond. Shortly after plasma bonding, pipette 0.5 microliters of polylysine into the bottom center port. The entire microfluidic circuit should be filled by capillary action within seconds. Then, leave it for a few minutes to fully coat the hydrophilic PDMS surfaces with polylysine. Next, Remove the unbound polylysine by aspiration-driven washing. Use a four-way union to connect the pump to the upper 3 ports with equal length tubing and start aspiration. Add PBS to the bottom 3 ports and wash for 1 minute. Subsequently, detach the tubing and remove any remaining PBS from the ports. Transfer the device to a microscope and heat using illumination to increase evaporation from the ports for rapid water mask formation. Inspect the device by microscopy to ensure water masking is complete. Then, insert stainless steel pins into the ports for coupling the plasma generated by a handheld corona discharge generator into the vacant microfluidic channels. Point the tip of the plasma source close to the tip of one pin and plasma treat the microchannel for 1 second. Afterward, remove the pins. Connect the 3 upper ports to the pump, start aspiration, and dispense PBS into the bottom 3 ports in order to draw PBS through the microfluidic circuit. Remove all PBS from the microfluidic circuit and leave overnight to complete biomaterial patterning. Here, the pattern is visualized using polylysine labeled with fluorescein. In this procedure, prime the device with appropriate media by adding 20 microliters to each of the bottom 3 ports. Then, use parallel aspiration from the upper 3 ports to rapidly fill the microfluidic circuit with media. Add 20 microliters of a disaggregated cell suspension to each of the flanking bottom ports. Use a syringe to gently aspirate from the upper 3 ports. Complete neuron arraying typically requires 1 minute. Then, using a pipette, harvest excess neurons remaining in the ports for arraying in subsequent microfluidic devices. This example shows how neurons are arrayed with single-cell precision. After that, submerge the device in media and place the device in the incubator for the cells to become fully adherent on the biomaterial pattern within a few hours. As with normal cultures, the media should be replenished periodically. To selectively treat either neuron culture compartment or the central neurite outgrowth compartment, dispense 20 microliters of the test substance into the bottom port connected to the channel of interest and aspirate from the port directly above. In this example, a selective treatment has been applied to the central compartment, and in this example, the flanking compartment has been treated. Treatments were established in 1 minute and were maintained for 60 minutes. The neuron co-cultures can then be monitored to measure the propagation of materials or pathology.
Once mastered, many microfluidic devices can be prepared in a single morning.
After watching this video, you should have a good idea of how to prepare the minimalistic neuronal cultures in your own labs, and use these to investigate mechanisms underlying material and disease propagation in the brain.